So potential energy, the first thing that you need to know for this concept and for this whole unit really is this really key concept that the sun is the original source of energy of all energy, of everything on Earth. And so you can see questions that will ask you that, where they'll ask you what is the original source of energy, and you always need to make sure that you say the sun is the original source of energy, because that's what it is. By definition, potential energy is latent or stored energy, and when we have changes in potential energy, this occurs through chemical reactions. So in the next clip, I'm going to go through a couple of examples that show this. So here's some examples that I want to go through with you as it relates to potential energy changes. So I want to connect this first to some information that you may already kind of be familiar with. And the first concept that we need to understand is this term called delta H, or enthalpy change is what it really means, or in other words, just a change in heat. So this is the notation that we use to describe an energy change or a change in heat or enthalpy change. And this can occur for lots of different types of reactions. So we have lots of different delta RHs, or heats of reactions, that we can refer to when we're doing chemistry. And it's very analogous to the example that I like to give, which is we've got lots of different vehicles that drive on the road. Now, all of them can be considered vehicles if they've got four wheels and we drive them on the road. That's typically kind of the generic term that we use for them. But we can describe them with a little bit more detail, like we can say that that's a Ford truck, or that's a Nissan car, or whatever kind of model or make that vehicle is. We can give more detail to what describes it. And so it goes as well with these heats of reactions that we can describe. So if we're talking about a heat of reaction, then that's just kind of really generic. It's just the heat for the reaction that the reaction is being described as. But if we specifically have a formation reaction, then we can call that the heat of formation. Or if we have a combustion reaction, then we can call that the heat of combustion, or the heat of decomposition. And these are the three kind of more common ones that you'll see in this unit. And so whether you see it say delta RH or delta FH or delta CH, you can understand now kind of the difference between those terms, and that these ones just give a little bit more detail in the sense that, hey, that's a heat of formation because that's a formation reaction. Now, something you have to be careful of as well is that if it's a decomposition reaction, you cannot use the heat of formation for that reaction, because a heat of formation is for a formation reaction, not for a decomposition reaction. Now, these two types of reactions you're really familiar with, and we've discussed them in previous classes, and it's just an endothermic reaction versus an exothermic reaction. And we know that for an endothermic reaction that heat is gained by the reactants. And for an exothermic reaction, we know that heat is lost, and that's kind of the net description of these two types of reactions. Endothermic has a net heat gain, and exothermic has a net heat loss. And so if these are just generic reactions that I've written up here on the board, just A plus B, if it's an endothermic reaction, what we have been used to doing is we say that if it's endothermic, the energy term goes on the product side, or sorry, the reactant side. And so A plus B plus, now in this unit, we can actually use numbers. We can actually calculate this amount of energy. In previous classes, really all we've written here in this spot is just energy, or something like that. But here we can actually put numbers in. Now, a new way that we can write these chemical reactions is we can write them in what's called delta H notation. And so that's what this is referring to up here. And this right here, this reaction is written in delta H notation, where we have the energy term written outside of the chemical reaction. Now, because it's not located in the reaction on either the reactant or the product side, we now have to use a sign, either positive or negative, to differentiate between which reaction type this is. Is it endothermic or exothermic? If I just write 100 and don't specify whether it's positive or negative, now I don't know whether this is an endo or an exothermic reaction. And so for endothermic reactions, the energy terms are positive. And it's because this much heat is being gained by the reactants to then form the products. And so I can write this reaction, endothermic reactions, in one of two ways. I can write it with the energy term written in the reaction, like you see here, 100 kilojoules on the reactant side. And over here, I can write it in delta H notation, where I go A plus B makes C plus D, and then the heat of that reaction is 100 kilojoules, positive 100 kilojoules, to indicate that the reaction absorbed energy. Now, if we come over here to exothermic reactions, the same is true, but you'll see that the energy term over here is on the product side. And so exothermic reactions have that energy term on the product side to indicate that this is how much energy has been lost by the reaction. And so we can write it as delta H notation as well, but you'll notice here that because it's energy lost or heat lost, that this 200 kilojoules must be a negative to indicate that it is heat lost. Now, something to point out here with these two reactions is that, and not necessarily typically for the endothermic, because the plus signs and the positive signs, they're basically the same, but over here, you can see I don't put C plus D minus 200. I just put C plus D plus 200. The location of the energy number in the reaction indicates whether it's endo or exothermic. The fact that this energy term is on the product side tells me this is an exothermic reaction. I don't need to stick negatives and positives. But for delta H notation, I have to have the correct term and the correct sign in front of that term. And so here, because it's endothermic, it's going to be a positive 100. Here, because it's exothermic, it's going to be a negative 200. And so this is the notation that we use for these types of reactions. And I got a couple examples, real life examples I want to run through with you in the next clip, so hang tight. So here's some real life examples that we're going to go through. You guys are familiar with already. First one is photosynthesis, and again, this is energy from the sun. And all of these reactions, the original source of energy of them is from the sun. But this one has got a direct implication to it in that plants absorb sunlight. And that is energy. And so when we're talking about energy being absorbed, this is an endothermic reaction. And so when we have plants that take in carbon dioxide and take in water through their roots and absorb sunlight through their leaves, they can undergo this process of photosynthesis and produce sugar, or glucose in this case. And then a little bit of oxygen as a byproduct as well. But if I were to write this as delta H notation, here in the red you can see that I still have the reactants on the reactant side, the products on the product side, but now instead of having the energy term on the reactant side to show that it's endothermic, I take it out, I put it over here as a delta H notation, delta RH equals, and then this has to be a positive number because it's endothermic, so positive 2,803 kilojoules. Both of these reactions would be considered exactly identical. If we take a look at cellular respiration, we know that cellular respiration is in basic terms kind of basically the opposite of photosynthesis, in that animals, for example, take in glucose or food into their body. They burn it by breathing in oxygen. That reaction takes place, produces carbon dioxide and liquid water. It's liquid water because in our bodies our temperature is 37 degrees Celsius, so that's not the boiling point of water, so it's liquid water. And then obviously it would produce the same amount of heat that's absorbed in photosynthesis. And this is energy in terms of ATP, if you have taken a biology class that explains that. And then this is the reaction written in delta H notation. Notice that this is exothermic because it's on the product side, and this is exothermic because it's a negative number. So you can opt to write these reactions in one way or the other, it's totally up to you, or you will see them written in one way or the other, and you have to be able to interpret both and know if you were given this reaction, that's an exothermic reaction, or if you were given this reaction, okay, that's endothermic because that's positive in delta H notation. Now, one other comparison that I want to draw here is the difference between cellular respiration and the combustion of glucose. If we're just combusting a hydrocarbon and it's not in, say, an animal body, then when this reaction takes place, because it's exothermic and the temperature is going to be higher, it's now going to produce not liquid water but water vapor. And so because it's water vapor here that's being formed as one of the products, it's going to change how much heat is released from this reaction. And so if I were to write this one as delta H notation, you can see for this one I know it's a combustion reaction, so I'm going to write delta CH in order to indicate that it's a heat of combustion, and then it's a negative 2,538.5 kilojoules for this reaction. So really the difference that you need to highlight in your notes for this is that the combustion of glucose produces water vapor, and the reaction cellular respiration produces liquid water. And those are some examples that you guys need to know, and make sure you've got them down in your notes. All right, so the last thing that we need to kind of go through here are just some calculation examples so that you guys have a bit of a grasp on what could be asked quantitatively to do when you're looking at chemical reactions and the heat that's involved with them. So the number one thing that we need to start off with is just a quick review on chemical reactions and what they mean. So we've got a balanced chemical reaction here, and what this essentially is just saying is that we have 1 mole of methane that reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water vapor. And that's a balanced chemical equation because we need the same number of elements on both the reactants and the reactant and product side of the equation. And then when this reaction occurs, this is how much heat is going to be produced. Now, because this heat is a negative number, again, that's an exothermic reaction, so we know that this is how much heat is being released. Now with that comes the understanding that then, okay, if I burn 1 mole of methane, that's going to produce this much heat. And if I react 2 moles of oxygen in this reaction, then it's going to produce this much heat. And if I make 1 mole of carbon dioxide, it's going to produce that much heat, and so on. So you kind of get the drift of this. 2 moles of water vapor would make 802.5 kilojoules of energy released for this reaction. And so what we can say here with this chemical equation now is that 1 mole of methane makes this much heat. We can use this information if we're given a question where we're asked questions about methane particularly, or if we're asked questions about carbon dioxide or water or oxygen for that matter. These 2 questions that I've got up here on the board ask questions about methane specifically, so we have some information here that we can use in this chemical equation to help us do these calculations. So if the question says, for example, you've got this many grams of methane, in this case it's 14.7 grams of methane, and you burn it, how much energy is going to be released? Well, remember in chemistry, everything goes through this concept of moles. We need to calculate how many moles of a substance we have because that's what our balanced chemical equation is basically in terms of, is these coefficients represent moles. Now, this equation isn't saying that we are burning 1 mole of methane, it's saying that if we burn 1 mole of methane, that's how much heat we would get. So how many moles do we actually have? Well, if I do this short calculation, that's a quick review from Science 10 and Chemistry 20, 14.7 grams divided by the molar mass is going to give me this many moles, 0.916 moles of methane. Now, this number here comes from this. What it means is that for every mole of methane burned, we get a negative 802.5 kilojoules of energy released. And so if I just take this number and multiply it by the kilojoules per mole, again, this is just unit analysis. I can cancel out just like I did right here, the grams, and left with moles. Right here I can cancel out the moles, and I'm left with kilojoules, and my answer ends up being negative 735 kilojoules of energy released when I burn 14.7 grams. Now you can have the reverse of this, where sometimes a question might say, hey, you released this much energy, how many grams were burned? And so that's what this second example is kind of going through. If we were to, for example, release 922 kilojoules of energy from this reaction, how many grams of methane was actually burned to make that happen? Well, I know again that I've got negative 922 kilojoules, and this time to cancel out the units, I've got my kilojoules on the bottom, and so my number has to go on the bottom because this is negative 802.5 kilojoules per 1 mole of methane. And so then I can just do the math here and I end up with 1.15 moles. And then again, canceling out the units, using the molar mass, I can convert the moles of methane into the mass of methane, and I get my answer of 18.4 grams for that question. And so these are calculations that you guys will need to know how to do when you are doing questions that relate to potential energy changes.